All right, let's talk about a math concept that trips a lot of people up: exponents. We're going to demystify it, and we're going to do it with a story. You'll see that when you really get down to it, an exponent is just a super powerful shortcut. Let me show you what I mean. So, our story kicks off with this little guy, an 8th generation purebred English Mastiff named Rickson. And he's actually going to help us find a simple pattern that leads to some surprisingly big numbers, and it happens way faster than you'd think. Okay, so like any puppy, Rickson has two parents. Super simple fact, right? We'll start there. One generation back, we've got two dogs. And, each of those two parents had two parents of their own. So if we go back 2 generations, Rickson has 4 grandparents. See that? We just jumped from 2 to 4. Let's just take it one more step. Each of those 4 grandparents also had 2 parents. That means Rickson has 8 great-grandparents. Are you starting to see the pattern taking shape here? So here's the key takeaway. Every time we go back another generation, the number of ancestors doubles. The pattern is just repeated multiplication. We're just multiplying by 2 again and again and again. Now, this is pretty easy for a few generations, but what if we wanted to think bigger? What if we wanted to trace Rickson's family all the way back, say 12 generations? How many ancestors would that even be? I mean, we could try to write it all out, 2 times 2 times 2. You get it. It's just long, it's messy, and honestly, it's super easy to lose your place. There's got to be a better way to do this. And that right there is exactly why mathematicians came up with a shortcut. It's called an exponent, and it was literally designed for this exact situation: repeated multiplication. So let's break this shortcut down. The entire expression, the whole package, is called a power. Just think of it as the complete thought that represents this whole multiplying over and over idea. Now, a power has 2 main parts. The first one is the base. That's the big number, the one you're actually multiplying. For Rickson's family tree, our base is 2, because everything is doubling. And the second part, that's the exponent. It's that little number up top, and it tells you exactly how many times you need to multiply the base by itself. So for our 12-generation problem, the exponent is 12. It's that simple. So instead of that crazy, long, messy string of 2s, we can just write it like this: 2 with a little 12 up in the corner. We'd read this out loud as 2 to the 12th power. So much cleaner, right? Okay, now here's a quick heads up on a super common mix-up. A lot of people will just point to that little number, the exponent, and call it the power. But you gotta remember, the power is the whole thing. It's the base and the exponent working together. It's a team. All right, so that's the basic shortcut. But this is where things can get a little tricky. This is where the shortcut sometimes turns into a trap. What happens when we throw in a classic math curveball? Negative numbers. You really have to pay attention here. Okay, let's start with an odd exponent, like the number 3. You can see here that whether the negative 11 is inside the parentheses or not, you get the exact same answer, negative 1,331. So with odd exponents, things seem okay, but don't get too comfortable. Whoa, but check out what happens with an even exponent, like 2. All of a sudden, those parentheses are everything. With them, we're doing negative 1 times negative 1, which gives us a positive 1. But without them, the exponent only hits the number, not the sign. So we get negative 1. That tiny little detail completely flips the answer. This table basically sums it all up for us. Rule 1, if that negative sign isn't wrapped up inside the parentheses, it's not actually part of the base. And rule 2 is the big one. A negative base with an odd power stays negative, but a negative base with an even power, it turns positive. Those are the 2 keys to the whole thing. So we've got all these rules about parentheses and negative signs, but you might be thinking, okay, why is it so important to get this right? Does it really make a difference outside of a few examples? Oh, it absolutely does. Look at this. This is a real question from a released Algebra 1 state test. You can see the laws of exponents are right there in the middle of it. This isn't just some random textbook problem. It's a fundamental skill you are absolutely expected to know. And get this, here's how students actually did on that exact question. Only 24%, that's less than 1 in 4, got full credit. And almost half the students, 45%, got no credit at all. This one little concept is a massive hurdle, which means if you can nail it, you've got a huge advantage. So let's lock in the big ideas. Number 1, exponents are just a shortcut for multiplying something over and over. 2, parentheses are absolutely crucial. They tell you exactly what the base is.
3, a negative base with an even exponent turns positive. And 4, a negative base with an odd exponent stays negative. That's the whole playbook right there.
You know, we started this whole journey with Rickson's family tree, but this idea of exponential growth, it's everywhere. You see it in money, in biology, in technology, you name it. So my final question for you is this. What other kinds of growth out there in the real world could you describe right now using the power of exponents?